Welcome to a short little video about how to compare the centers of two samples using R. The steps are very familiar to what they were for drawing conclusions about the mean of a single sample. You have to ask yourself, what is the parametric test? What are its assumptions? Do the data violate those assumptions? And then, if the data do violate the assumptions, you have to use the non-parametric test. If the data do not violate the assumptions, you get to use the parametric test. Same situation as before, slightly different question. School zones have reduced speed limits. Even when children are not present in Stillwater, that speed is 30 miles per hour. Question: do cars travel at the same average speed through Zone A and Zone B? Notice we're comparing the average speed in two zones. That's what makes this a two-sample test. Zone A, Zone B, comparing their means. So it's means two sample. Here's the research hypothesis. The average speed through Zone A is equal to that of Zone B. That's my research hypothesis. Because it's got an equals part, it's either an equals, less than or equal to, or greater than or equal to. That's also going to be the null hypothesis. Alternative will be the opposite of equals. The opposite of equals is not equal. So here's the test. We want to do a two-sample t-test. That's the parametric test. Its assumption is that the data in each group are generated from a normally distributed population. To do that, we're going to use the Shapiro-Wilk test on each group. If both groups pass the Shapiro-Wilk test, we get to use the two-sample t-test. If either group fails, we have to use the non-parametric test. And that non-parametric test here is the Mann-Whitney test. So let's see how this actually works in R. R started up, already imported the data, already attached it, already have a summary, should already look familiar to us. First step, we need to test if the data in A and the data in B come from normally distributed populations. So we'll do a Shapiro-Wilk test on the Zone A group and a Shapiro-Wilk test on the Zone B group. Run both. We see that the Zone B is not normally distributed, that the data in Zone B did not come from a normal distribution. Zone B data fails the assumption test. Therefore, we can't use the two-sample t-test. Even though Zone A passed, Zone B didn't. Therefore, we have to use the Mann-Whitney test. The function for the Mann-Whitney test in R is wilcox.test, takes Zone A, Zone B, and then the alternative. Here the alternative is not equal. In R, that's two-sided. Interesting thing is, in R, the default alternative is two-sided. So we can include this part or we can exclude it. We'll get the same answer both ways. Control R. P-value is 0.01571. We reject the null hypothesis because P is less than alpha. We conclude that there is a difference in the two average average speeds through the two zones. Cars in Zone A do not travel on average at the same speed as those in Zone B. There's some difference between the Zone A and the Zone B cars, or the markings, or some other aspects of School Zone A and School Zone B. Okay, we rejected the null hypothesis. Now the question is, how much different are they? How much different is actually a question of a confidence interval. It's going to be wilcox.test, Zone A, Zone B, and then we have to specify that we want a confidence interval. Now let's look at the 95% confidence interval. We're 95% confident that the difference in average speeds between those two zones is somewhere between 2 miles per hour and just about 0. The number on the left is 2. The number on the right is just a little bit less than 0. So the average of A minus the average of B, it's because A came first, is between negative 2.000067 and negative 2.189227 times 10 to the negative fifth. It's pretty close. Again, we've got that warning message down at the bottom. I give you permission to ignore that. In class, we explain why. So we've got the hypothesis test. We've got the confidence interval. So the two differ somewhere between no difference at all and about 2 miles per hour. So it's not a big difference. We were able to detect a difference, but it's not practically that significant. Now a box plot. Zone A, zone B. I'll plop the box plot over here. Notice the box plot doesn't actually include the labels at the bottom. We have to tell R what we want those labels to be. The slot is the names slot. Since we're going to give it two values, we have to enclose it in the C. Zone A, zone B. That's better. Of course, we still do need to do the Lab 3 requirements. Notice again that it does break up into 3 different realms. You got the par realm, you got where you're actually creating your first plot, and then you've got the annotation you're adding to it. There's some other things that we can add to the plot. If we do PCH equals 16, watch what happens to the outlier dots. We can color those outlier dots. We're going to color them purple. That's outcol, O-U-T-C-O-L, for outlier color. We could color the boxes. Colored it Alice blue, which is a very light blue. We could do light blue. We can add a lot of things to it, but this is good enough for now. So for this one, we were trying to compare the means of two populations. We wanted to use a two-sample t-test. That's the parametric test. It's more powerful. It's better able to reject a false null hypothesis. The assumption of that two-sample t-test is that the data in each group separately came from normal populations. So we had to use the Shapiro-Wilk test to test that. If it passed the Shapiro-Wilk test, if both samples passed the Shapiro-Wilk test, we were able to use the two-sample t-test. If either one failed, or both, we had to use the non-parametric test, which was the Mann-Whitney test. Hopefully this was helpful. Have a good day.